This Xilinx ZYNQ 7000 is a fantastic, real-world example of the programmable SoC, or PSoC, architecture we just looked at. It beautifully illustrates the concept of combining a standard processor system with flexible, programmable hardware on a single chip. Let's break down this diagram. You can see it's divided into two main sections: the processing system, or PS, and the programmable logic, or PL. First, let's focus on the processing system. This is the hard part of the chip, meaning its components are fixed and manufactured into the silicon. At its very heart, you can see the powerful dual-core ARM Cortex-A9 processor. Having two cores means it can run multiple tasks simultaneously, which is great for performance. Each core has its own instruction and data caches, and they share a larger L2 cache, which helps speed up memory access significantly. Also within the PS, notice the wealth of built-in components. We have memory controllers for connecting to external memory like DRAM and flash. There's also a block of on-chip memory for very fast data storage. And look at all those standard peripherals listed on the left: USB, UART for serial communication, I2C, SPI, and even Gigabit Ethernet. These are all common, pre-built interfaces, so you don't have to design them yourself. Everything in the PS is connected by a high-performance AMBA interconnect, which is the communication backbone. Now, let's look at the other major part, the yellow block labeled programmable logic. This is the FPGA fabric of the chip. Unlike the fixed PS, this section is a blank canvas. It contains a huge number of resources like logic gates, DSP blocks for intensive math calculations, and RAM blocks. As a designer, you can configure this area to create any custom hardware you need. Perhaps you need a specialized video processing engine or a unique industrial communication protocol that isn't included in the standard peripherals. You can build it right here in the PL. So, how do these two worlds, the PS and the PL, talk to each other? That's the most powerful feature. They are connected through high-speed AXI ports, which are part of the AMBA bus system. This allows the software running on the ARM processor in the PS to control and exchange data with the custom hardware you designed in the PL. This tight integration lets you accelerate software functions by offloading them to dedicated hardware, giving you the best of both worlds: the ease of software development and the performance of custom hardware. The bullet points on the right neatly summarize these key features: a dual-core ARM processor, on-chip memory, various memory interfaces, a rich set of integrated peripherals, and the all-important programmable logic, all tied together with EXI buses. This specific chip is what we'll be using for our design projects, so understanding this architecture is the first key step. We've made our way through the foundational concepts of system-on-chip design. We started by looking at the motivation for this design framework. Then we weighed the advantages and limitations of SoCs. We also examined the entire SoC design flow, from concept to final product, and just recently, we explored the idea of a programmable SoC or PSoC. Now, as you can see highlighted, we're arriving at a very practical and hands-on part of our journey: design a simple ARM-based SoC. This is where we'll take all the theoretical knowledge we've accumulated and put it into practice. We're going to transition from discussing what an SoC is to actually building one. This section will be the culmination of everything we've learned so far. We'll be using an ARM processor, which is at the heart of so many devices we use daily, as the core of our own custom system. We'll see how to connect it with other essential components to create a complete, functional system on a chip. So, let's get ready to apply these concepts and dive into the design process. Now we get to the really practical and exciting part: designing our own simple ARM-based system on chip. The overall goal here is to take all the concepts we've been discussing and actually design an SoC, then create a working prototype of it on a ZYNQ chip. Remember from our previous discussion, a ZYNQ is a type of programmable SoC, which makes it a perfect platform for this kind of hands-on development. So, what are the building blocks of the system we're going to create? This page breaks it down into 3 core components. First, at the very heart of our system, we'll have an ARM Cortex-A9 microprocessor. You can see it in the pink box at the top of the diagram. This is the brain of our entire operation. It's the component that will execute our software, process data, and control all the other hardware blocks on the chip. The Cortex-A9 is a powerful and very popular processor core, which is why it's used in the ZY&Q chips we'll be working with. Second, we need a way for the processor to communicate with everything else. That's the job of the EXI bus. In the diagram, this is represented by the thick gray bar in the middle, labeled ARM AMBA AXI system bus. Think of the EXI bus as the superhighway of our chip. It allows high-speed, efficient communication between the microprocessor and all the other components. EXI is part of ARM's AMBA standard, which is the industry standard for connecting blocks within an SoC. The third component is a collection of customer-made physical IPs. IP stands for intellectual property, which in this context means pre-designed hardware modules that perform a specific function. The customer-made part means we'll be creating some of these ourselves. These IPs are the peripherals that give our SoC its specific capabilities. If you look at the diagram, you can see exactly how these pieces fit together. The Cortex-A9 processor is the master. It connects to the EXI bus, and hanging off that bus are all our peripherals. We have blocks like DDR RAM, which is our system's main memory. There's a UART for serial communication, perhaps to a computer. We have GPIO, which stands for General Purpose Input/Output, for controlling simple things like LEDs or reading buttons. We also see VGA and HDMI for video output. And that last block with the 3 dots is very important. It signifies that this is a modular and extensible design. We're not limited to just these peripherals. We can design and add our own custom hardware to the bus to create a truly unique system tailored to a specific application. So, this page provides the blueprint for the project we'll be undertaking. In the upcoming modules, we'll dive deep into each of these areas: the Cortex-A9 architecture, the EXI bus protocol, and how to design and integrate our own custom IP cores. This page serves as a roadmap, giving us a preview of all the exciting hands-on work we'll be doing in the upcoming modules. We're going to take all the concepts we've discussed and put them into practice to build a complete, functioning system on chip. Let's break down what you'll be learning to do. First, we'll start with the fundamentals. You'll get a deep understanding of the ARM Cortex-A9 processor architecture, which will be the brain of our system. Alongside that, we'll learn about the AMBA AXI bus protocol. Think of the EXI bus as the superhighway or the nervous system inside our chip. It's the standard that defines how the processor communicates quickly and efficiently with all the other components like memory and peripherals. Once we have that theoretical foundation, we'll move into software development. You'll learn to use a professional tool called the ARMDS5 development suite to write and run a simple software application on the Cortex-A9 processor. This is your first step into programming the hardware. Next, we'll combine hardware and software. You'll implement a basic ARM-based SoC from the ground up. This means taking the Cortex-A9 processor core, adding some essential embedded peripherals, and connecting them all using the EXI bus. Most importantly, you won't just be designing this on a computer. You'll be prototyping it on a real hardware platform, a programmable SoC or PSoC from the Xilinx ZY&Q family. But we won't stop at just using pre-existing components. A key part of becoming an SoC designer is creating your own custom pieces. You will actually be developing your own hardware peripherals, your own custom logic. Of course, once you build a piece of custom hardware, you need a way for the processor to talk to it. So, you will also develop the specific software drivers for these physical intellectual property blocks, or IPs, that you create. This is where you really experience hardware-software co-design firsthand. Finally, you'll demonstrate all of these new skills by building a fantastic final project, a real-time video processing application. Look at the images on the right. The goal is to take a live video feed, like the HDMI input showing the seals, and feed it into the SoC you designed on the ZYNQ chip. Your system will process every frame of that video and perform an edge detection algorithm on it. The result is what you see in the bottom picture, the VGA output. Your system will output a video that only shows the outlines of the objects. This is a powerful demonstration that proves your entire system, the processor, the bus, your custom hardware, and your software drivers, is all working together perfectly. It's a very practical and visual way to see the power of the SoC you've built. This final page lists the bibliography, which is essentially a list of recommended books and resources that will help you explore the topics from this course in much greater detail. Think of it as a guide for your further learning. The first book listed is ARM System-on-Chip Architecture by Professor Steve Ferber. This is a foundational text in the field. To give you some context, Professor Ferber was one of the principal designers of the original ARM microprocessor. So, this book is written by someone who is instrumental in creating the very technology we're studying. It's an excellent resource for understanding the core principles and architectural philosophy behind ARM processors and how they are used in system-on-chip designs. It gives you the why behind many of the design choices. The second book, the ZYNQ book, is a more modern and practical guide that's directly relevant to the hands-on work we discussed. It focuses specifically on embedded processing with the ARM Cortex-A9 on the Xilinx ZYNQ 7000 all-programmable SoC. As we saw on the previous slides, the ZYNQ platform is what we'll be using to prototype our designs. This book is a fantastic, step-by-step companion for that process. It bridges the gap between the theory of SoC design and the practical reality of implementing a system on a real, modern programmable chip. So, to summarize the two resources, the first book by Steve Ferber gives you the classic, fundamental architectural knowledge. The second, the ZYNQ book, provides a very practical, hands-on guide for the specific hardware and processor, the ARM Cortex-A9 on the ZYNQ 7000, that you'll be working with in the upcoming modules. Both are extremely valuable if you wish to build a strong expertise in this area.